So good evening and good morning, everyone. I am Salah, a researcher from Berkeley AAP, and today I'm going to hold the 52nd TrustML Young Scientist Seminar. But before we start, allow me to briefly introduce RIKEN AIP. So the full name of the institution is RIKEN Center for Advanced Intelligence Projects. It was founded in 2016, and it was at the beginning a research center for the next AIP projects. It is led by Professor Sugiyama, and today RIKEN AIP is a center that conducts Japan's leading AI research. It aims to enhance AI fundamental technology and tackles real-world applications. In addition, our center encourages the collaboration with various researchers and engineers in related fields, and we will be very happy to host you here in our offices in Tokyo in the near future. Today, just before we start, I would like to remind you that the talks is recorded, but we will check with Sasha whether we can upload it on YouTube later on. But for now, no reproduction is allowed unless you get the express authorization from the guest. So let me briefly introduce our guest. Sasha is a last year PhD student at Berkeley. He's advised by Jitendra Malik and Amir Zamir from EPFL. His work is in representation learning from embodied AI, and in particular, he's developing intermediate representation that supports sample-efficient downstream learning and lifelong calibration. His work has received a CVPR Best Paper Award, a CVPR Best Paper Honorable Mention, and an NVIDIA Plenary Research Award. His research was also placed first in the CVPR Embodied AI Navigation Challenge. And today, he will be presenting his recent work about robust learning via cross-task consistency. Thank you very much again, Sasha, for joining us today, and the floor is yours.
Wonderful. Thanks so much. That was a very nice introduction. I think I didn't need to list all the awards. Just the research is enough. Also, please upload this to YouTube. You can reproduce it as much as you want.
Thank you very much.
Also, please interrupt me for questions. Hopefully this can be somewhat of an informal talk. The Berkeley way I've learned is to have very aggressive questions in the middle of the presentation. So if I don't see that, I'll assume that things don't make sense and I'll try to elaborate more. So please, if stuff's unclear, just ask me. And if I don't see it in the chat, go ahead and just unmute yourself. So this is robust learning through cross-task consistency. So something that I've learned in my PhD is that in practice, machine learning is almost always part of some downstream system. And there are usually many different predictions. I mean, in self-driving, Tesla makes like 40 different predictions of the underlying scene and then uses these for some downstream decisions. In robotics, you might estimate depth or point clouds as surfaces or objects, and then use those for decision making. And this is really the type of thing that I'm familiar with, but I also assume that if you are even just training like a classifier for something to serve ads, you're going to make a decision about whether to serve an ad or not. So this is a way to try to make these different predictions consistent because they all reflect some shared underlying scenario. So we didn't come up with this idea of consistency. It has a really, really long and really glorious history in computer vision and machine learning and NLP. So I couldn't even begin to try to enumerate all the papers, but I'll try to just give some examples. One is cycle consistency in machine translation. The idea is you know your translation is successful if you can translate it from one language to another and then translate it back. And I learned recently that the middle box here is not English, it's Japanese. So I think it also is interesting because it's not always clear what the cycle consistency would be in this case. Is it the language of the text or is it the phrase English? Then there's other things like in tracking, cycle consistency through time. If you want to track an object in a video, you can track it forward and then you can reverse the video and track it backward. And you know that the start and the end point should be the same. And then it's been really, really fruitful in neural networks because all of these different consistency terms can be used as self-supervised losses. So one nice example is using stereo views and left-right consistency in order to estimate depth, because you can track correspondences into different frames, then you can triangulate depth based on that. So this paper is in that vein, and the core insight or idea is that if you are estimating many different things, the room layout, the segmentation masks, the edges, they all reflect the same underlying world state. So those edges in the image in the bottom right had better line up with whatever the segmentation mask edges are in the bottom left. And that's a learning signal. And so we tried to come up with the most generic form that we could think of that would still be useful. And the way people usually train models to make multiple predictions now is you try to train them independently to just optimize some sort of pixel-wise loss in computer vision, for example. So you can train a depth estimator, and a really good one, Midas, is shown on the top. And you can train a normal estimator, and so that would be shown on the bottom. And, oh, well, the slides are slightly out of order, but that's fine. And we know that these things are related. The normals should be the gradient of depth. And so you can do the finite differences on the depth image, and you get this sort of right middle image. And you can see that it's different than the prediction that was made from the normal estimator. And so that should give us some signal. These two things are not consistent, and that could be used as a loss. The way people usually try to address these multiple predictions, or the naive way, is to just put these things into a shared network and pray to the deep learning gods that the network will learn some representations that produce consistent predictions. But this doesn't really happen. And what's even worse is like these predictions from the multitask network are often worse than if you had just trained the things independently or trained smaller independent networks. And of course, I'll bring receipts. There's a paper that shows this at ICML, but I think anyone who's trained a multitask network in this way has seen this phenomenon. So we wanted to come up with a generic way to enforce consistency that would actually work for multitask learning. If you know what these constraints are, like that the normals is the gradient of depth, and it's differentiable, you can try to enforce that as a regularization loss. So GeoNet is an example that does this for normals and depth. Let me just pause to ask questions. Is like are normals and depth clear here or not? Because I can explain what these predictions are supposed to show, but I've already used the term a bunch.
Could you please elaborate what are the actual tasks here and how you can estimate the error? Thank you.
Yes, thank you. I love the feedback. So the top task is depth estimation, monocular depth estimation. And the task here is for each, given the input image on the left, produce an image on the right where each pixel contains the metric depth of how far away that point is in 3D space from the camera. And you can usually train this on data sets that have, labels or labels from a depth sensor or are generated from some sort of static data. So common data sets for this are things like Kitty or NYU. And the best model for this right now is something like Midas that doesn't use depth, but it uses inverse depth or disparity. The bottom task here is surface normal estimation, where each pixel isn't how far away the point is, but it's the vector normal to the surface of that point. So if you actually have the depth, you can then figure out what the surface normal should be by trying to fit some plane to the depth at that local neighborhood and then estimate the normal. So in that sense, the normal is the gradient of depth, and you can undo the gradient to get the integration to go from normals to depth. So these are example tasks that I'll return to, but the method isn't specific to those. But GeoNet is specific to those. It uses these analytic constraints as regularization losses in order to train two networks such that the normals are not just correct, but produce the right depth. And the depth is not just correct, but produces the right normals. And again, you can kind of see the same failure mode where now like the results might be consistent, but they're not correct. This is the same problem we saw in multitask learning with the shared encoder. So we wanted to address that, and we did so through cross-task consistency. And the idea was, instead of using these analytic constraints, which we know for normals and depth, what if we just learned a neural network to try to predict one prediction from the other, and then use that as a constraint? It's more generic because then we don't need to know the analytic constraint. And also the gradients are often nicer because neural networks have had a lot of work go into them so that the gradients flow through the network and they work nicely as regularizers. So I showed some examples of predicting multiple things from the same RGB image, but the idea is general. You could predict multiple things from different sensors or different representations of the same underlying state. So here, this is on the top camera view of a gel site sensor. It's a touch sensor. And on the bottom is the actual reading from the sensor. And what this oval shows is the deformation of the silicone from the wire. And the idea is the same here, right? You can see the wire in the camera. You know that the wire is touching the gel site sensor. So you kind of know how the silicone should be deforming. Although it would be really difficult to write it down analytically, a neural network could learn to predict whatever the gel site reading should be from the camera that's looking at the manipulator. And what makes this different than the slide I showed before is here, the two sensors are not just the same RGB image. They're different representations of the same underlying scene. The contribution, I think, of cross-task consistency is coming up with a way to train this, because this is a really natural idea. And there's so many instances of people taking this idea in a specific domain and making it work really well. So we needed to do a couple things here. And now let's start to talk about the method. But is this setup clear? That you could use this for other predictions, not just normals and depth?
I think it is.
Okay, good. And if it's not, please interrupt me with questions.
But is it only for two tasks, or is it something that
Great question.
can be extended?
Yeah, it can be extended for any number of tasks. And I can talk more about how I would extend it for large numbers of tasks, but the solution that I'm going to introduce first, it scales quadratically with the number of tasks. So if you have 5 tasks, now you need to train 5 times 4 different pairs of regularization constraints. And I think there are ways to get around this, but yes. Okay, so the first thing we try, which seemed obvious to us, was if you're training this depth estimator and you want to read it out into normals, train it so that you predict the depth and then you read the depth into normals, and then you apply a loss where the predicted normals are close to the ground truth normals, or the read out normals are close to the ground truth normals. And the way we set this up was first we trained a neural network fully supervised to predict normals from depth. Then we froze this network, and so it's shown with a dotted line, and we used it as a regularizer for the RGB to depth network. So the training setup is we take an RGB image, we feed it through, it predicts depth, we apply a loss there based on the ground truth, and then we read the depth into normals and apply another loss there. And that's what this image is supposed to show on the left. And so there are 2 really big problems here. The first is that you're using the ground truth normals to supervise the depth estimator. So now you need a data set that has annotations for all of these different tasks. I mean, in this case, it's RGB depth and normal. There are some data sets for those, but I mean, I don't think Kitty has that. And if you have like 5 or 10 different predictions, quickly you run out of data sets, or the data you can use to train this is like quickly becoming smaller and smaller. So that's issue 1 in these triplet data. Oh no, data is duplicated in line 1. The second issue is that there's this problem where if your depth normal readout is not exactly accurate, now your RGB to depth network has not just to produce the correct depth image, it has to correct for whatever the imperfections are in the normal readout. So it has these competing objectives: address whatever shortcomings are in the neural network that reads it out, and also produce a ground truth depth. And it's not necessarily the same prediction. So you have these competing objectives. The idea was to use a perceptual loss. And I'm going to talk a bit about what a perceptual loss is. It started with it's used often in like image generation, where you want to produce images that look like real images. But the idea is really, really simple. Instead of reading out the predicted depth and comparing it to the ground truth normal, you read out the depth and compare it to the read out depth of the ground truth normal. So you want your depth to look like ground truth depth, at least as it's perceived by this normal readout. And so This actually alleviates both problems. First, this perceptual loss doesn't depend on the ground truth normal, so you don't need this triplet data anymore. And then second, it doesn't give you a competing objective because it's fine if the normal is imperfect, as long as it's imperfect in the same way that the ground truth normal or the ground truth depth read into normal is imperfect. So the perceptual loss here is the first term. And then so the way we got to this perceptual loss was sort of by having the idea, and then we justified it by taking this triangle loss, which is the basic thing where you read out the depth and compare it to the ground truth normal. That's the second term. And we applied the triangle inequality. And we get the first term, which is the perceptual loss, and a second term, which is constant with respect to the RGB to depth estimator. And so we don't actually need that second term at all. So the derivation is you have this triangle loss, you change it to a perceptual loss, and then you can apply one perceptual loss per other prediction. You could predict normals, you could predict curvature, you could predict segmentation masks, edges, whatever. I'll have some experiments discussing this. And the full loss is just the sum of all these different perceptual losses. And so in one stage, I'll talk about the training data set too. Actually, I'll talk about the training data set now. So that's the method. It's a bit mathematical. I probably should have given examples, but I will give some examples later. For this, the training data set is the taxonomy data set, which is another paper that we had years ago. It's a data set of indoor spaces. And for each of the indoor spaces, we generated a bunch of labels so that for every view, you had annotations for a bunch of computer vision tasks. Segment depth, like we talked about, normals, like we talked about, edges, both like a canny edge detector run on top of the image or occlusion edges that show you where there are discontinuities in the depth image, segmentation masks, and some others that I can't see because the Zoom thing is covering the screen. But if any of them appear and you guys don't know what they are, let me know and I will define them for you. So this crosshouse consistency thing that I've mentioned uses a perceptual loss in order to read your prediction out into some other task. Normals is a supervised task, but you could just as easily do it with the self-supervised task, where you estimate something from the RGB image, like edges or key points. And then you enforce that your predictions also enable you to recover these edges and these key points. This is really helpful for taking this pixel-wise loss that we use for surface normals and making it capture things that are structural to the image beyond just pixels. Because these normals have to be read out into the appropriate edges and key points, it forces the normal estimator to recover these fine-grained details and the important bits of the scene for like manipulation or something. And it can be done in this fully self-supervised way because you can get these 2D texture edges from the RGB image. Or you could do it with supervision. You could read the normals out into reshading, which is like what you would get if you had a light and moved it around and got rid of all the colors. It's like the idea of intrinsic image decomposition in computer vision. Or curvature, which is something like the derivative of normals. We talked about edges, and you can also try to read out like depth from normals or something. So this shows the result of an RGB to normal estimator read out with crosshouse consistency applied in order to read out the normal prediction into all of these other domains. And the different rows show different methods. So the middle line is learning with crosshouse consistency. The top line is what happens if you just train a RGB to normal estimator. And you can see that it's not as good at recovering the fine-grained details of the wine glass on the table and the vases in the background. And so this is just a chart showing the numbers behind the intuition that I tried to give. If you train a model to estimate reshading in this case, it doesn't actually read out into these other domains properly. As you optimize the reshading prediction, the perceptual losses on these other tasks remains high. but by optimizing these other perceptual losses during training, we can reduce them. So the point of this graph is just to show that it works. You can optimize the thing you're trying to optimize. And this is a video showing the same thing, that if you just train all these different networks independently, you train your depth estimator, you train your curvature from depth estimator, you train your normals from depth estimator, you train your reshading from depth estimator, and you just naively glue them together, that's the result in the bottom row. And you can see that the results are really noisy. They make predictions of very high curvature in regions like on the wall where there should not be high curvature. But when you train with these perceptual losses, the flat areas stay flat. Does the idea here make sense or not so much?
So far, so good, I would say. But
okay, good.
I don't see any questions or comments, I would say, in the chat. So
I see. Cool. I didn't see the one message, but then I see it was you. So thank you for writing in the chat. And then we compared it to a bunch of other consistency-based methods. And you can probably guess what it's going to show because this is the figure. Probably it's going to show our method is good, but it works. So we compare it to the shared encoder approach, and the top two images are from images that are in the test set of taxonomy. So everything should be good there. And then there's two other images that are just taken from the internet, a black and white image and another image of an scene. And the cross-task consistency approach is better able to recover the fine-grained details compared to these other consistency approaches like the shared encoder multitask network or cycle-based consistency. It does better than the baseline perceptual loss, which here is just using a pre-trained image net encoder. I think it's just AlexNet, where you want the prediction and the ground truth to be close in terms of the latent features of SC7 of AlexNet. That's the baseline perceptual loss. The baseline L1 UNet is the unit that we trained with no sort of consistency. GeoNet is the normals that were trained using the analytic constraints between normals and depth. And I think that the most interesting comparison in this figure is the comparison between GeoNet and cross-task consistency, because GeoNet is using the ground truth relationship between normals and depth. And so that's in some sense an upper bound for how good this learned approximation could be. But in practice, we found that the learned approximation is often better than the analytic regularization. And I just chalk this one up to the fact that neural networks produce nice gradients. That being one reason. And the other reason being that the perceptual loss means that you don't have to correct for the problems in the imperfections in the neural network. So we have some numbers to back this up. I am happy to discuss the numbers later on, but this is by far the biggest table that I've ever put in the paper. And I spent so long getting the structure right that I would like to never look at these numbers again. And I think numbers are not really fun in a talk. But if we want to talk about particular experiments, I will go back to this and discuss it later on. So those are the comparisons. Now that we've got those out of the way, I think one interesting thing that we saw from training with cross-task consistency is by adding these extra losses and constraining the predictions. Actually, I'm going to back up for a second. The first thing we saw from the numbers was that often the predictions would be better, even on the task you cared about, after applying these consistency constraints. So if you wanted to estimate depth or normals or something, then adding these constraints would help a bit. Not always a lot, but they would never hurt the depth estimation, and they would always make you better at these downstream tasks. So in some sense, it really just is a constraint optimization problem. You're taking this prediction and you are making it obey some constraints, and cross-task consistency is a way to then train your thing to actually obey those constraints. Sometimes it helps with the objective at the top, but the most important thing is making the constraint satisfied. And so that's really what this method is focused on. And by adding these additional constraints, the network can then generalize better to other distributions or things that it hadn't seen during training. Messy bedrooms that were never seen in the training set because the training set is like usually collected by like real estate agents who clean up the scene a lot before going in with their cameras and scanning. Or it works on paintings of indoor spaces like a bedroom in Arles shown on the top, or disaster sites shown on the bottom. And then we have some numbers of how well the thing generalizes to other data sets besides what it was trained on. So NYU is a depth and surface normal data sets. We trained our thing on taxonomy and then evaluated it on NYU. And cross-test consistency outperformed the other methods numerically. And the bolded lines show things that are statistically indistinguishable. So the consistency-based method generalized as well as the thing trained using the analytic constraints, GeoNet, and as well or better than the baseline UNet. And definitely better than the multitask train network, which has a much higher mean angular error for surface normals. We have numbers on other data sets as well that I don't want to go into, but hopefully I've convinced you that the neat trick using a perceptual loss works. And so now we'll talk about how we train this whole thing. Let's say that you have an RGB image, X, and you have a bunch of other predictions that you want to make, Y1, Y2, Y3, Y4, Y5, whatever. You now have YK squared, effectively, constraints. How do you train them all? I mentioned before that we started by training each of these individual things first just in a fully supervised way without any cross-task consistency. So you train a Y1 to Y2 estimator, which is shown by F Y1, Y2. Then when you want to train X to Y1, you freeze everything else and then only update that one edge. And then you just sort of round robin. The way we picked it was we picked the triangle that had the strongest constraint violation, optimized that for 10,000 steps or something, and then just iterated. And so that's exactly the algorithm here. You pick the most violating triangle, train that one, and then just do this until convergence. We also experimented with trying not just triangles, but constraints that have path length longer than one. And we found that really triangles capture give you most of the juice. I mean, you can try training things so that X to Y1 to Y2 to Y5 is close to X to Y5, which is the thing shown in the third panel here, but triangles give you most of the juice.
But how do you define violating triangles?
Just whichever has the highest loss. And then I guess it's a question of like, maybe you have like a cross entropy loss and maybe you have an L1 loss.
Yeah, because each task has different loss, so it's hard to compare them, I mean, or to pick.
Yes, it definitely is. I think we just did this by normalizing it compared to whatever the ground truth, like direct prediction loss was, and taking like a ratio of like the indirect to the direct approach. I mean, that's not perfect. It still doesn't account for different tasks or like the different types of losses, but for us, it was good enough. And we did have different types of losses. They weren't just L1 pixel-wise losses. There were also some like cross-entropy losses for semantic segmentation.
I see. Thank you.
But it definitely requires some domain knowledge here. And honestly, like, I think there's no way around it because some things are more important for your decision than others. So there will always have to be some weighting, like weighting of the different losses. Now, if I were to do it today, I probably wouldn't take this pairwise loss approach. I'd probably take something like a multi-MAE, which is a follow-up from my advisor, Amir Zamir DPFL, which just predicts all to all. Transformers weren't around at the time when we first did this paper, so we weren't able to mask out different types of input domains. But the way I would do this is I would, the advantage of this approach is that you have shared weights, so you can try to update all the tasks maybe simultaneously, and you don't need to have all of these n squared predictions. And the way I would do it is first I would train the mass autoencoder to do all to all or pairs to pairs. And then I would use the pre-trained version as the perceptual loss for the new iteration. So I would take this pre-trained thing, and then in step one, I would take RGB, predict semantic segmentation, and then I would have forced the perceptual loss so that the semantic segmentation read out into all the other domains simultaneously, instead of having to pick one triangle and train that at a time. And then once step one had converged, I would take that, make that the perceptual loss, and then train step two, and do this until convergence. So it's just an efficient way to pack together all of these different edges and make this training more optimized. But anyway, either method works. One is a little more efficient. Both of them, I think, would work. And they produce these consistent estimates. So that's one aspect. The other aspect that I'm really excited about is now you're not just estimating normals directly, you're estimating normals with many intermediate domains. And all these different predictions should be consistent with each other, in that the predictions of the normal at some pixel need to correspond and be the same between all the different paths you could take. And the variance, in some ways, is a measure of uncertainty, because some of the paths will succeed, some of them will fail, and it gives you a measure of how badly the whole system is performing. And this is just a video to make that explicit. The top row here shows the normals read out from a bunch of different paths, from curvature to normals, from depth to normals, from reshading to normals. The depth to normals, I think, gives good intuition, because small imperfections in the depth prediction produce drastic changes in the direction the local normal is facing, which is why it looks so noisy in the third column, first row. And after the crosshouse consistency training, the normals are much more similar in the bottom row. And based on, you could just concatenate all of the different images, take the variance within each spatial location, and that gives you a measure of uncertainty. So we call that consistency energy, because it's sort of a task agnostic way, or somewhat task agnostic way, to measure the uncertainty of the system. And so we can look at this consistency energy both by training everything independently, this is the baseline model, or using a shared encoder, this is the multitask model. And both of them have pretty high energy. And the cross-task consistent method, or the conservative model, does optimize this over the course of training. So to give an example of what it looks like, you can feed it a query image. This is the normal prediction from the direct path, and the consistency energy shown spatially per pixel. And the consistency energy is really high in areas where some of the paths got it right, and some of the paths like dropped one of the legs of the chairs. So the consistency energy is high when the networks are starting to fail, which is exactly what we want in order to measure where the system's not working. And it also works for like out of distribution things like images, where this wall on the right-hand side is not perpendicular to the wall right in front of us, and this is out of distribution. And so the network is making predictions that it's really uncertain about, and that shows up in the consistency energy. And so I sort of alluded to this through the talk, but this can also be used as a measure of domain shift. So this video here shows inputs to the network with increasing amounts of JPEG compression, more than anything seen during training. And the plot in the bottom right here shows the consistency energy at these different levels of compression. Now, it's not perfect. If the energy is higher on one image, it doesn't guarantee that the loss will also be high. But in distribution, it's roughly correct, and it gives you some measure of if you've shifted from what the networks are expecting to see. So we thought this was really cool. And we thought maybe, well, one, we did some experiments to see if this is correlated with the loss, and that's shown on the left-hand side. We did some experiments to see if this could be used to detect whether it's being evaluated on a data set different than what it was trained on. So we trained it in domain on taskonomy of indoor spaces, and we evaluated it on outdoor scenes driving Apolloscape or Doom, which is a video game. And it was able to detect this. There's a bunch of other ways you could detect this that are probably more sample efficient, but this just emerges from defining these consistency constraints. And it can also be used to detect continuous domain shift. And it's a very generic approach. I mean, if I wanted to detect whether I was in Doom or taxonomy, I would just define some color detector because the colors are very different. But cross-house consistency can be done not just for images, it can be done for touch sensors or audio or you name it. And then we can try to also use this consistency energy as like a self-supervised loss so that on this new data set, you can try to minimize the energy and hope that the network then updates its predictions to make them consistent and hopefully more correct. And that's what shows the error. That's what this is supposed to show, that the error pre-adaptation and post-adaptation. And it works a little bit. I don't think it's the best approach, but it works a little bit. And I think it works especially well if you can also define some additional constraints. Like if you want the consistency to be correct, and you want the color distribution of the predictions to be roughly identical to what you would expect. So as you can identify more constraints, then the consistency error optimization tends to work better. That's just something we found. And then there was a follow-up paper that we had, cross-domain ensembles. And I think my colleague, Teresa, came to give a talk on this earlier, so I won't belabor the point. But in case any of you weren't here before, the idea of the paper is, one, you have all these different predictions, and you have some uncertainty error. Can you calibrate this so that the uncertainty is actually well calibrated with the error? And Teresa and Ozan did a really good job of developing a way to do this by then calibrating based on some validation sets. They call it sigma training, and it works really well. And you can not just calibrate the errors and get good estimates of the true uncertainty, it also tells you the weights that you should use to merge these different things, or how much you should weight each of these different paths in order to merge the things into a final prediction. And doing so works really well. Here's a video of the standard approach, a single model, and the standard approach for uncertainty estimation using neural networks, or one standard approach, deep ensembles, where you just train with different random seeds, and then you merge the predictions that way. And that's in the middle prediction column. And the cross-domain ensembles approach is shown on the right-hand side here. And the way that I read this video is that there's a lot of flickering in the single model approach, and there's still a lot of flickering from the merged deep ensemble approach. But there's not a lot of flickering, it's more stable in the thing on the right. And that's really what we want to see for this task. So they're both more accurate, and there's less jitter as the camera moves around. The predictions are more stable to minor perturbations of the input. And we have numbers to back it up. This is the average L1 loss over 11 unseen distortions or middle modalities from the common corruptions datasets. And with numbers, I feel like numbers are always boring because you know what it's going to show. It's going to show your method works well. But we compare to a lot of other types of merging approaches or multitask approaches, and this worked quite well. So with that, I would like to open up for any questions that you guys have, either clarifications, or we ran a bunch of experiments that I didn't talk about that I would be happy to discuss, especially if they come up organically. But I'll pause for questions here.
Thank you very much, Sasha. Yes, so feel free either to ask, to speak up, or to write on the chat. I received 2 questions on the chat already, but so I had a question: what are the cases where task consistency works best and cases where it doesn't? I don't know if something that you studied.
Yeah, that's a great question. I think the cases where it works best are where the 2 different predictions have a lot of mutual information, because then you have a really strong regularization constraint. So depth and surface normals are just a wonderful example. We were surprised by how closely linked a lot of things were. If you have like the 2D key points of an image, you can pretty accurately reconstruct the surface normals, even though it'd be extremely difficult to write that down analytically. The networks could learn this. And so that worked really well as a constraint. Where it really doesn't work well is that there's not a lot of information. So object classification and surface normals is something that doesn't work well as joint regularization, because like knowing there's a cat in the image does tell you a lot about the shape, but you just don't know where in the image it is. So I would be really interested in coming up with a way to sparsify this big cross-hash consistency graph into only the edges that are meaningful. And I think there are some ways you could do this using some notion of how related the tasks are. You could do this by hand. You could do it automatically using the task distances from taskonomy. Or you could try to learn them for whatever your domain is by doing some transfer learning and seeing how good one representation is for predicting another.
Okay, so if I understand well, it could be used to drive which task we need to collect more labels for to improve the learning, maybe. So we just do it with small samples, and then we can increase the data sets.
Oh yeah,
Yes.
I think that's a great idea too. I was mostly focused on the predictions, like which predictions should you be enforcing consistency between. But it could definitely also tell you how well your direct prediction on those other tasks are doing and drive or guide you to collect more samples. I think that's a fantastic idea. I had thought about that.
And we go to questions about the loss, the cross-task consistency loss. How do you balance the contribution of the perceptual loss compared to the original loss?
Yes, this is a wonderful question. I had this lambda fudge factor here, but we did need to do something to balance the different perceptual losses. So the regularization losses were generally pretty easy to balance with the main loss by just tuning lambda. It wasn't super sensitive, but the different perceptual losses often had gradients of different magnitudes. So we weighted the different perceptual losses by the inverse of the magnitude of the gradient, so that the perceptual losses that had very large gradients weren't washing out all of the other tasks. The exact way we do that is in the appendix, but then we had another term outside, which is how much do we weight all the perceptual losses relative to the ground truth. And that was really easy to tune. We could just use like 1 or 0.1 or 10, and they all worked pretty well.
Oh, so it reminds me of the weights that you used for the taskonomy paper. I think. Okay, so it's very similar.
Yeah, I think you could use that too.
I actually had a question of my own. Because my research is mostly about adversarial robustness. I was wondering if you feel that this approach could also improve other types of performances. So you mentioned generalization to other datasets, but maybe also adversarial robustness.
Oh my gosh, absolutely. Fantastic question. I think it does. This cross-domain ensembles paper has a bunch of experiments focused on exactly that. Especially the merging will increase adversarial robustness, but also the cross-hash consistency loss will on its own improve adversarial robustness. But I didn't want to mention this too much because I know Teresa gave a talk and I didn't want to be too redundant. But absolutely, generalization and adversarial robustness. And I think really it is a better fit for that than it is for generalization, because cross-hash consistency is focused on local perturbations, which are the same thing that are adversarial.
I see.
Although cross-hash consistency is not focused on worst case perturbations. It's focused on the natural perturbations.
I don't know if there are any more questions.
Okay, well, if anything comes up, I'm always happy to answer more questions over email. Or if you find me at a conference, I love talking about my work, so happy to discuss.